I did in my professor friend video, or actually in fembiology, in one of the courses I've taught in this institute. I talked about integration and um, the fundamental theorem of fembiology uses the concept of integration rather, and sort of integrating function of femininity, I think, and sort of proving that it's sort of um, gay. I think I forgot. I kind of forgot. I suggest you guys check it out. It's there in the course, the fembiology course. It's a complete course, and if you guys want to uh, have a rigorous or sort of a serious education on fembiology, a more rigorous one than the ones offered by Professor Lando at the Ligma University, you guys can check out my course on fembiology, or LOSC's course on fembiology. So just a little warning, it needs a little bit of math. If you plan to sort of study the course and get a degree in fembiology, you're gonna need a little bit of math, especially some calculus, maybe a little linear algebra, a tiny bit of quantum mechanics, because we use some quantum mechanics in there. Um, and fembiology is just basically an integration of various studies from queerology and in queermatics here in LOSC. So if you guys want a very serious actually, a very serious and rigorous study of the femboy community, or that or the LGBTQ community in general, or a more serious version of Professor Lando's lectures on femboyology, you can check out that playlist. So okay, um, promotion's over. Let's talk about integration. So I sort of already discussed what the derivative is. I'm gonna make another video which goes in depth on what the derivative is, but I gave you guys the basic principle or a definition of what a derivative is in my differential equations video, or exposition rather. And integration is the opposite of the derivative. So the integral, which is denoted by this swoopy s, is the inverse or the opposite of the derivative, which is d over dx. And just to note, the act of finding derivative is called differentiation. I didn't mention that in the derivative video, but now that you can know that, you know differentiation, we differentiate something. We find the difference, or rather the rise of a run, or the difference of a small nudge in the y direction compared to a difference or the distance or small nudge in the x direction, or actually the y direction caused by a small nudge in the x direction, or difference. That's what's called differentiation. We're finding the ratio of two differences of points, and rather not only that, but what they approach as our x approaches zero, or as our difference in x gets smaller and smaller and smaller and smaller, but not infinitely small. So yeah, in this lecture or this exposition, I'm gonna be discussing about the polar opposite of this, which is integration, where we bring a graph together. So we're gonna start with the one-dimensional case, where we have a line. We have a line, or a number line. Let's say number line, not an interval. This is an interval. All right. And so we want to find the integral of this this line between two certain points in D. I'm not gonna list zero. Maybe you can make a zero or b zero, and then this a is a negative integer. So we'll stick with the integers for now. So I'll make this a z, just so that we don't complicate stuff with rational numbers, because fractions are sometimes a pain in the ass to work with. So let's work with integers for this case. For the 2D, let's say we want to find this line over here, and it's not exactly an area, because area isn't intrinsically 2D and 3D thing. It requires space, and this doesn't have space. It's just a line. So in reality, when we use integration to find the area of a one-dimensional line on a one-dimensional axis or number line, it's really just finding the distance between 2 points. So we're trying to find the distance between A and B. So the absolute value of A minus B, or B minus A. And so how do we prove that? How do we prove that? Using calculus. So one way of doing that is to take this interval here, this closed interval, A to B, and split it up into tiny little intervals. I'll make this big so that you can see it. And then there. You can split it up into various intervals, and then the distance between A and these intervals, I'll call these intervals x sub 1, x sub 2, x sub 3. The distance between these guys, we're going to add those distances to get the distance between A and B. So we sort of x1 minus A plus x2 minus A, x minus 1, I think. So we're trying to find this. So we're trying to find this interval here. So x minus 2 minus A minus x minus A, x1 minus A. Or rather, I mean, it's actually just this minus this distance. So we're trying to, okay. So it's actually x minus 2 minus x minus 1. So it starts with this distance, we know this, and then this is x2 minus x1, and then x3 minus x1 plus x2. Then and then sort of b minus this 3 minus x1 plus x2 plus x3. And what's important is that what's really important about integration is that these intervals, or these small tick marks we produced on this number plane, are evenly spaced. So the distance here is the same as the distance here, is the same as the distance here, is the same as the distance here. And it's just basically we divide this into this amount of intervals, which is 4. But what integration does is not only splits them, but it finds their behavior, or finds the limit as these intervals increase and as their distances between each other, these small x2 minus x1s, grow smaller and smaller. So we know that this plane is just y equals, this is 1, let's say 1. It could be any arbitrary number, but really we're just focused on the x-axis here. So integral is really just 1. So since I said in the beginning that integration is the opposite of differentiation, this time when we're given a function, we're trying to find that functions, or what function is a sort of has that function we're given as a derivative. So we're trying to find something called an antiderivative. And the act of finding an antiderivative is integration, or anti-differentiation, but we just call it integration because it's less cumbersome to read, and it really brings home the intuition on how it works. Now I can ramble all about Jacobian matrices and the actual way of thinking about these guys, but at an intuitive and at a high level, for the one who's just starting calculus, it's great to think of it as the area under a curve. So you guys know areas, right? You guys know areas as this shaded region of a shape. If we're given a side and a length, the area is just the side times the length. In the case of a square, it's just s squared, where s is the side, right? And if we're given a three-dimensional object, we're finding the surface area, because we're trying to find the area of the surface. If we were to unfold this cube and find out or add up the sums, add up the surface areas of each face that we unfolded from the cube, that's our surface area. Now going back to our one-dimensional case. Our function that describes this entire line here, including a and b, is simply just y equals 1. And we're trying to find, actually it's an arbitrary value, but I'm gonna pick 1 because because a function whose derivative is 1 is x, right? So the x over dx is 1. So the integral of 1 is x, right? So we're just gonna do the opposite of differentiation, and we denote integration by this swoopy s over here to mean sum. So we're adding up these small intervals that we split this interval into. So we're integrating this function 1 or dx because the differential of x is just dx is just dx. So 1 times dx is just dx. You can just sort of ignore 1, but it's still there. 1 is still there. This is not 0. Otherwise, I'd note it. So we're integrating that from a to b. So we're just saying that we're adding up an infinite amount, not really infinite amount, but a very large amount of small intervals, evenly spaced intervals within this interval a and b. That's what this integral sign tells us. And the dx over here actually has two roles or two interpretations. The more abstract interpretation is to think of this dx as what variable we are integrating with respect to. So if we integrate with respect to y here, and we think of this y as a sort of two-dimensional function z, then we just get 0 because x, we're not integrating with respect to x. Like it sort of works like differentiation, such that if we're integrating with one variable and we have another variable, we treat that variable as a constant, right? So that's that. And the second one, or the most intuitive one, is that this dx is the length of each interval, or rather the spacing that I'm talking about. So these things over here, these spacings between this x1, x2, x3, is dx or delta x. We call it delta x because it's the change in x, and that delta x is when I introduced you guys the formal definition of an integral or a definite integral, that's what it is. And so that's dx, or we just denote it as small dx because as dx approaches here, as these intervals get smaller and or these spacings get smaller and the intervals increase in size, dx shrinks and becomes dx. Like how when we find the derivative, delta y over delta x becomes dy over dx. And that's something I'm going to discuss in the derivative video. Actually, after this, I think I'm going to discuss vectors again. But yeah, this is why it's point. So we're just trying to find a function that whose derivative is 1, and that's x. And what we do is sort of do this thing, this notation here. And this notation tells us to evaluate x from b to a, or from a to b. And that simply tells us plug b into the equation and subtract that by the thing we get when we plug a into the equation. So that's b minus a. And as you can see, it lines up with the distance formula, which is b minus a. So let's say we have a 0 here, right? This is the distance of a, and to find the distance between a and b, we just subtract this part from the entire thing. Alright, so that's the two-dimensional case. How about that's the one-dimensional case. How about the two-dimensional case? Now, this is where my saying, or what I said about area under curves, is important. Now you guys know how to find the areas of very simple geometric objects such as triangles, rectangles, parallelograms, what else? Rhombuses, kites, stuff like that. Even obtuse triangles, even acute triangles, equilateral triangles. You guys know how to find the areas of those. The areas for these geometric figures are already sort of fleshed out during your high school years or your grade school years. But what if we have some irregular shape? What if we have a continuous shape? Because these polygons that I discussed, that I just said, are discrete shapes. They have a definite roughness to them which is precise. They have a certain preciseness to them. But what if we have a very smooth curve? Like say x squared, a parabola. Let's say we have a parabola. Let's name it there, x squared. Let's say x squared. What if we want to find the area under this curve? Like here, like until here. We want to find this shaded region. How do we do that? I mean, we can't just sort of use the equation or the formula for a triangle. I mean, yes, it does look like a triangle at small distances, but this is not an efficient way of approximating the area of this curve, because it's a straight line and this is a curved line. Its slope changes at every point, unlike the slope of points at the hypotenuse of a triangle. So how do we find the area under this curve between 0 and this thing over here, a? Well, we find the integral. So this is the function of this, y equals x squared. And to find the area under this curve is to find the antiderivative. Like I said a while ago, it's like adding up or chopping this up into tiny intervals, but instead of tiny like lines, this time we're chopping it up with a bunch of tiny boxes. So like that. This is just a small approximation. It's not the actual thing. So there. We're chopping it up into tiny little boxes and then finding the area of these boxes and adding those areas. That's what we're doing here when trying to find the area under a continuous curve. And this is actually, I believe this is how a majority of mathematicians actually derive area formulas for those simple geometric and discrete shapes that you guys know about. And so, yeah, like I said, the dx is just simply the width of these rectangles, this small sliver over here. And the function is just the height at this point, or in this interval. And the height is just, it's the same as this part here. It doesn't change because it's a rectangle, for Christ's sakes. And the idea of an integral, really, the overarching idea of, not really overarching, but like the most intuitive way integrals are taught, or rather how I'd like to think of it, or how a majority of mathematicians would like to think of it, or teachers, is that with these rectangles we have, what we want to do is make them smaller and smaller and smaller and proportionally increase their size. So we sort of cut this up some more. We cut it up some more and increase the amount of them, or decrease their size, so that when they get smaller and smaller and smaller and more of them, it becomes more continuous. It looks more like the curve itself. It's like adding stairs to a stair to make it look like a slide, right? Or a curved surface, like a slide, yeah. Slides are possibly made or designed with integrals in mind by approximating what the shape of a stair is, and then adding more stairs in between those approximations to get a more smooth shape. And this is the basic premise of the definite integral. This is the basic premise of what we call Riemann sums. And it's named after the mathematician Bernard Riemann. And it's the rigorous definition of what we're talking about here. So the integral from a to b of f of x, our function dx, is equal to the limit as n approaches infinity of the sum from I equals 1 to n of f of x sub I times delta x. And like I said a while ago from delta x, and so this delta x over here is actually the spacing or the width of each of these rectangles we're trying to add up. And so, and this f of x sub I is the length of each rectangle we're trying to add. Thank you. Ice cream's good. Okay. Okay. And so this sum here tells us to add up these rectangles, or the areas of this rectangle, to approximate it. Okay. And this x sub I is b delta x is b minus a over n. And x sub I is a plus I delta x. Excuse me. Okay. Yeah. We plug this this small thing into the function. That's basically the intervals here. Each interval we get here, or each point over here. And we're trying to find the corresponding length of each width. And that's the width is this delta x. Well, that's why delta x is inside here, because we're plugging this, right? And from there, finding the height of each rectangle corresponding to its width. And this limit here basically tells us what this function goes to, or what this entire thing goes to, as we have more and more rectangles. So this n represents how many rectangles we have, and we're just trying to find out the area that we get, or what number we get, or measure we get for bigger and bigger, or more and more rectangles. Okay. That's that. That's integration. Oh man, this ice cream's really good. They make a damn good ice cream in the Philippines. Okay. That's that. So, alright. We want to find the area between a and this. And so basically this entire function diverges to f of b minus f of a. I'm not going to put the proof here. There are many other videos out there that actually show you the proof. So it's not necessary for me to sort of give you guys the proof here. You guys can just search up the proof for this, and then that's that. But this over here is the fundamental theorem of calculus. That's what it is. The tissue stuck. Okay. Oh. Okay. I know a teacher's not supposed to eat while in the middle of lecturing, but this ice cream just came out of the blue. And how am I supposed to deny it while I'm doing this? It seems disrespectful for me to have denied it. Right. This is what it is. This is what I was talking about a while ago. About plugging A and B and then into f of x and finding their difference. Alright, so for this case, we just need to integrate x squared dx from a to b. And we're finding a function whose derivative is x squared. And this is a quick thing. D over dx of 1 cubed, 1 over 3 x cubed is actually x squared. So that's our antiderivative. We could compute this out of here by eliminating some variables, but this is our answer. Or actually, it's not answer yet. That's a definite integral, sorry. Which is integrated or evaluated from a to b. Wherein b is just a and a 0. So that's 1/3 a cubed. Because the term where we plug 0 in just vanishes. 1/3 a cubed. Yeah, I guess that's it. Next video, or next exposition, I'm going to talk about different derivatives. I know I'm supposed to discuss derivatives before I discuss this, but you guys can just pretty much watch it first. In fact, I'll put in the description that I'll give you guys a warning in the description to watch the derivative episode first, or exposition, before this. Alright, so that's the first exposition. See ya.